Hi, we are Group 10. Our project is about to designing and optimizing a 3x3 sober edge detection filter using high-level synthesis. We implemented a filter in Python, converted it into C++, and synthesized it for FPGA using Vivaldo HLS. The optimization techniques like loop pipelining, bit width reduction has helped us improve performance and resource usage. Let's take a look at how we did it.
To design a sober filter, firstly, we convert the input image into data files using Python coding. After the conversion, we can see that all the pixel values of the input image has been saved in this file. Next, we import the OpenCV library to use a built-in function to create sober filter. By input the image file into the code, we can compare the original image and the sober filter image. The extraction of edges from the image has proven that the code can be functioned well. For C coding, the sober filter is designed using matrix Gx and Gy shown. The magnitude for matrices is using absolute value, and magnitude are kept between 255 and 0. By opening the output file generated, we are going to visualize the output from the C code. The image shows similar result as the Python coding, as the edges has been extracted too. This has proven that the C code works. For baseline design, the estimated time used is 2.825 nanosecond and 16 clock cycle. And also, this is a summary of the resource usage. Using the RTL generated previously in Vivaldo, we can see that the slide is 7.973 nanosecond and the total on-chip power is 0.473 watts, which is a combination of dynamic and static power. The I/O usage is 11%, which is ratio of 28 out of 256 of utilization.
After verifying the basic functionality of our sober filter in C++, we move on to performance optimization using the Vivaldo HLS. We apply two optimization methods in our project. One, we focus on speed, and another, we focus on the resource effective. For optimization method 1, like previous I mentioned just now, we focus on the speed, so we have made some several changes to both in the source code and the test bench. Now we focus on the source code first. We optimize the bandwidth by including the ap_integer.h library. Since the image pixels value range is from 0 to 255, so we only use 8-bit integer for both input and output data. Additionally, we use only 3-bit integer for the variable GS and GY, as their possible value range is from -2 to 2. This significantly reduces the resource uses without affecting the accuracies. Now we also apply the array partitioning. Specifically, we partition the GS and GY array completely along their dimensions. This allows the parallel access to each element, improving the performance by enabling the simultaneous operation. Lastly, we use the loop unloading. Since the number of loop interactions was small, so we apply the full unloading to escape all interactions in parallel, in further to increasing the processing speed. Now we focus on the test bench code. We first apply the bandwidth optimization by using the 8-bit integers for both input and output data, consistent with the source code. Additionally, we use the 10-pin intelligence for the loop index variables. Since the image dimensions are 512 multiplied by 512 and 10 bits are sufficient to represent the value up to 512. Then we also apply the array partitioning to the image and the output image array by setting the partitioning type to complete and specifying the dimension as 2. This means each array is split around the y-axis into 3 parts, allowing the parallel axis and the faster data process. Furthermore, we apply loop pipelining to enable concurrent execution of the nested loop. Since the main loop contains 3 inner loops, so the pipelining allows that to run more effective and reduce the overall latencies. Lastly, we apply the same load unloading strategy as in the source code, so it can enable full unloading for small loops to improve the parallel and the execution speed. Now let us talk about the result of the optimization method 1, which focuses on the improving processing speed and the throughput. Although the estimated code period increased slightly, but the latency was reduced, which led to the significant improvement in the maximum throughput. Next, I will show the result of the resource users, power consumption, and timing stats, and explain them using our summary table. Now, let us move on to optimization method 2, which focuses on improving the resource effectiveness. In this method, we apply the bin wave optimization to reduce the unnecessary logic by assigning only the requirement number of bits of each variable. Unlike the first method, which prioritizes speed, this approach aims to balance the performance with hardware users more effective. This is because the techniques used in the method 1 like pipelining, loop unloading, and array partitioning, it will significantly increase the resource consumption. Optimization method 2 avoid those and making it more suitable for systems with limited hardware resource. Let us take a look at the result of the optimization method 2, which aims to reduce the hardware resource. In this version, the estimated clock period is 2.808 nanoseconds with a latency of 16 seconds. Next, I will show the result of the resource users, power consumption, and timing slash, and explain each using our summary table. From this table, we can conclude that the optimization method 1 achieves the higher throughput, even though it has the largest estimated clock period of 5.607 nanoseconds. This is because the clock cycle interval is reduced to adjust the force cycle, allowing the design is to process the data much faster. Additionally, optimization 1 shows the higher Fmax is in Vivado at 751.88 MHz and the largest throughput at 44.59 million pieces per second, making it the fastest among all 3 versions. Overall, the optimization 1 is the best choice for maximum speed and performance. Optimization method 2 show a slight improvement in performance compared to the baseline. It also achieves a shorter estimate execution time, higher throughput and a better timing slice. Referring to table 2 and 3, we observe that while optimization method 1 results in increased resource and power consumption, optimization method 2 significantly reduces resource usage, particularly in terms of the lookup tables, which are fundamental components of the combination logic in FPGAs. A decrease in lookup table usage shows a more resource-effective design. Furthermore, optimization method 2 maintains the power consumption at the same level as the baseline, making it both energy and the performance enhanced. Based on the data presented in the table, we can confidently conclude that the design objectives have been successfully achieved.